Hi, my name is John Krockmalny, and I've developed these visual tutorials to accompany any type of training format that might be delivered. In this presentation, I'll introduce several troubleshooting methods commonly used by electrical technicians. There are three learning outcomes associated with this presentation. Number one, test current overload protection devices. Number two, utilize voltage drop method troubleshooting methods. And number three, utilize electrical ladder diagrams for troubleshooting. Overcurrent protection devices can come in the form of fuses and circuit breakers. Electrical circuits can fail in two ways: as an open circuit and as a shorted circuit. When circuits short out, they have no resistance to the amperage flow. This amperage, under a short circuit condition, achieves a very high value, technically an infinite one, and if not protected, causes damage to the circuit and personal injury. Overcurrent protection devices have an amperage rating, whereby if the circuit exceeds its value, in the case of a short circuit, the fuse or the circuit breaker will open and protect the circuit from damage. These devices offer no resistance to the circuit, but are considered conductors. Also, fuses and circuit breakers are required by the National Electric Code. Here in this graphic, we see a 120-volt circuit having two loads, an M load and a green lamp. These two loads are controlled upstream by various switches. Notice that the amperage in branch 1 is 3 amps and in branch 2 is 1 amp. Because this is a parallel circuit, the total amperage in this circuit is 4 amps and is found between L1 and terminal 1 and between N and terminal 2. As mentioned earlier, overcurrent protection devices protect the circuit if it ever becomes shorted. Notice a fuse rated for 5 amps is installed between terminals L1 and 1. If this circuit ever has amperages of greater than 5 amps, this fuse will open to protect the circuit. Fuses are common devices investigated in troubleshooting. In this graphic are pictured two fuses. Fuse A on the left is good. Fuse B on the right is open. A multimeter configured to read resistance can be used to determine fuse condition. As mentioned earlier, a fuse is considered a conductor. When applying a resistance configured multimeter across a good fuse, the meter will read very little resistance. This is a typical value when reading the resistance of any conductor. A fuse opens when amperages exceed its rated value. Notice that the fuse on the right is open. Applying a resistance configured multimeter to read this open fuse gives us a value of OL, or open line. In this case, this is an open fuse that needs replacing. We can also perform a voltage measurement to check the overcurrent protection devices. In this measurement, the circuit power must be applied so that the meter can read it. When doing so, make sure to wear the proper personal protection equipment as specified in the NFPA 70E standard for electrical safety in the workplace. When multimeters are configured to read voltage, the leads are placed across the fuse and the voltage values are read. Using this method for overcurrent protection assessment, if the meter displays zero point 0.0 volts, the component is good. There is found no pressure difference between the voltage entrance and exit of that fuse. If the meter displays line voltage, in this case 120 volts, the fuse is open and needs to be replaced. Before we get into the voltage drop method of troubleshooting, let's examine a fluid power circuit. With any fluid power circuit, problems can occur. Using a method called a pressure drop examination, We first apply the power to the unit. By making the fluid power circuit operational, we can compare the actual conditions to what they are supposed to be doing. In this graphic, we see a parallel fluid power circuit with two paddle wheels powered by a pump. When the pump is activated, notice that there's a difference in pressure resulting in the flow of fluids, causing the paddle wheels to spin. If we have a differential pressure meter, we can read 120 psi in this system. Using this differential pressure meter, we can measure 120 psi to the right of the pumps and to the paddle wheel loads. Also notice that certain numerical points are identified in the diagram, L1 on the discharge side of the pump, N on the suction side, etc. 120 psi exists on L1 terminals 1, 3, 4, and 6. Using the same meter, we can measure 0 psi to the left of the pumps and the paddle wheel loads. Terminals N, 2, 5, and 7 have 0 psi, indicating these positions. This is the difference in pressure allowing the flow to be initiated. In this graphic, we see a non-operational fluid power circuit caused by a plug installed between terminals 1 and 3. This plug represents total resistance and stops the flow of fluid. Notice the pressure differences. 120 psi measured at terminals L1 and 1. This is the pump discharge pressure. 0 psi is measured at terminals 3, 4, 6, 7, 5, 2, and N. This is the pump's suction pressure. We could logically conclude that the obstruction to flow is located between terminals 1 and 3. It is between where there was pressure measured and where this pressure disappears. Energy can be converted from one form to another. Therefore, fluid power circuits behave much the same way as electrical circuits. This is where we can understand and apply the voltage pressure drop method of troubleshooting. Like the fluid power system, the electrical circuit is energized and placed into operational mode. Then we compare the actual circuit conditions to what the conditions they're supposed to be in. In this diagram, we see a 24-volt AC parallel ladder diagram with its power applied. Notice that the M1 load, located between terminals 4 and 5, and the LT1 lamp between terminals 7 and 8 are energized and working. Taking a voltage configured multimeter and referencing the C terminal with the black lead, we can touch around the circuit with the red lead of this operational system and record the voltages. Between terminals R and C, we measured 24 volts AC. Between terminals 1 and C, we also see 24 volts AC. Between 3 and C, there is also 24 volts AC. Notice that between terminals 5 and C, 2 and C, 8 and C, there is 0 volts. This is what we can expect with an operational circuit when powered. There's a voltage drop across each load when energized. Notice in this same ladder diagram, there is an open circuit between terminals 1 and 3. This results in a non-operational circuit. The M1 and the LT1 loads are not energized. By applying the voltage drop method of troubleshooting, energizing the circuits are tested with a voltage configured multimeter to find specific areas where the voltage appears and disappears. In reference to the C terminal, voltages appear at terminals R and 1. In reference to the C terminal, voltages disappear from terminals 3, 4, 5, 6, 7, 8, and 2. From these measurements, we can determine that the problem is between terminals 1 and 3. The problems are between where you measured the voltage and where this voltage had disappeared. Here's another ladder diagram whose loads are not working. Doing the voltage drop method of troubleshooting, we see in reference to terminal C, 24 volts existing on terminal R, but this voltage disappears on terminals 1, 3, 4, 5, 6, 7, 8, and 2. Notice that there's a break in the conductor between terminals 1 and R. Using the voltage drop method of troubleshooting, the opens of a circuit is found between where the voltage appears and where that voltage disappears. In this graphic, we've got a circuit that is only partially working. Notice that the green light, LT1, is illuminated, but the M1 motor is not. Logic tells us that there is nothing wrong with the branch 2 circuit energizing the LT1 load, and we can ignore this in the troubleshooting process. Doing the voltage drop method of troubleshooting on branch 1, referencing terminal C, we measure 24 volts AC on terminals R, 1, 3, 4, and 5. This voltage disappears on terminal 2. The problem is between terminals 5 and 2. Notice that there's an open conductor at this location. Some ladder diagrams may be more complex, but the process for troubleshooting using the voltage drop method remains the same. In this 120 volt AC ladder diagram, we see a working system. With this working system, notice the voltage drops. This is what allows the flow of amperage to be initiated, powering the loads. Let's apply what we've learned so far. We now have a problem with this circuit. Nothing is working. We can use the ladder diagram to help us determine the problem while we're using the voltage drop method. Referencing the N terminal with our voltage configured multimeter, we record the actual voltage measurements. Analyzing the circuit, we then list the expected voltages at each terminal if it's working under a normal condition. Once completed, we compare what the actual condition is doing compared to what it's supposed to be doing. Notice that referencing terminal N, on terminal L1 we measure 120 volts AC, and on terminal 1 we measure 0 volts. We now know that the problem keeping the circuit from operating is located between terminals L1 and 1. The problem is always between where you had the voltage and where this voltage had disappeared. Looking at the ladder diagram, we see that the F1 fuse is located in that position. Testing this fuse, we find that this fuse became open, preventing the amperage flow and needing to be replaced. The voltage drop method of troubleshooting is a common method used by technicians finding circuit problems. Remember, to do this method, circuits have to be energized and placed into working order. Using the multimeter in this application, the meter is configured to read voltage, and the meter's black lead is placed on the end of the circuit. In this example, terminal C. This is the reference for the readings of the other terminals.